feel kind of physicsy, and the reason that we're doing this is the connection between so probably the most commonly used model for studying vibrations is the simple mass spring system. So these are called simple harmonic oscillators with and without damping. It turns out you can use exactly the same model to study what are called RLC circuits, which are circuits that have capacitors and inductance. So we're going to derive the model for the mass spring system from the ground to show you that actually the reason that we were studying differential equations with constant coefficients is that they show linear differential equations with constant coefficients are maybe the core model. It turns out things vibrate. So, and then we'll talk about some of the different ways the solutions can behave. I'm not going to go, the notes that I wrote are pretty intense as far as like, hey, look, if this specific type of relationship between the coefficients gives rise to these specific solutions, the way we're going to do this is we're going to derive the model, and then we're going to look at some equations we've already seen before, and then interpret them in a physical setting. So instead of memorizing giant tables of solutions, which I don't want you to do, I just want you to be able to look at one of those and say, hey, here's an equation describing a mass spring system. Describe the system and describe the long-term behavior of the solutions. Okay. All right. So the problem that we're trying to solve looks like this. So we have a mass of m kilograms is attached to a spring of natural length little L0 with spring constant K. Spring constant K. At time t0, the mass is displaced y naught meters and released with velocity v naught meters per second. Find an equation of motion. So the question one is find an equation of motion. Question two is analyze the solutions. So the idea here is not that we're going to go through the reason why all these physical laws hold, but that if we assume Newton's laws and Hooke's law, that we can extract an equation that is like the mass spring equation, the equation that determines the behavior of a simple harmonic oscillator. And then we can use that to sort of study different sort of solutions that can arise based on different assumptions. A picture of what we're doing here looks something like this. So we have a spring. Its natural length here is L naught. So with nothing attached to it, that's the natural length of the spring. If we attach the mass to it and it gets stretched out, so here's the mass m. If it's not moving, and we call this the equilibrium position, so this is where the mass wants to sit without oscillating, we're going to call this y equals 0. So this is a y-axis. Y is going to tell us the position of the mass relative to a scale where we put 0 at equilibrium. Yep.
L0 is it without the mass?
L0 is the natural length of the spring. Yeah, without the mass. And then we're going to have a different quantity here called big L0, which is the displacement above the natural length to get to the equilibrium length. Okay, so that picture right there, nothing is moving.
So y0, the displacement isn't from
Y0 is relative to the 0 of the y scale, right? So the mass right here would be at position y is equal to 0. If the mass was down here instead, its position would be whatever y naught happened to be, right? That's y naught is position relative to the equilibrium position. Oftentimes, it's nice to see what we mean. One of the things we're going to consider here is damped oscillation. And so a pretty natural picture for a damped oscillator looks something like this. You have an additional massless stick hanging out the bottom with like a plunger attached to it, and it's sitting inside of a hydraulic vat, and there's some kind of fluid inside there. And so this is resisting the motion of the spring is the idea. As the spring moves up, this pulls back and tries to resist the motion. As the spring goes this way, you have resistance in this direction. If you want a physical model that looks like this, so here we're thinking about this as a damper. This is essentially how the suspension of your car works. So car suspensions have two components. There's a spring that bounces in response to you going over bumps and through holes. But you don't want your car, I don't know if any of you have actually driven a really crappy car before. I had terrible cars in college. And when you go through a pothole in a car with a bad suspension, it just bounces and keeps bouncing because the springs don't stop, right? They just keep oscillating. So attached to the spring in your car is a hydraulic damper called a shock absorber. And what it does is it resists the motion of the spring. It eats the energy of oscillation and sets it back to equilibrium. So what we're going to do is we're going to analyze all the forces that are at play in this system. We're going to add them all up, and what's going to fall out the other side is a second-order linear differential equation with constant coefficients. So, forces on the mass. So there's 1, gravity. That's pretty easy. Because I am assuming the positive direction is down, the force due to gravity is just mg.
Positive y is down.
Positive. This is the positive direction, and this is the negative direction. So we're orienting this so that otherwise the negative signs get annoying, right? So, okay. If you like, here's your mat. You guys could construct yourselves a giant free body diagram if you want. There's mg pulling down. Okay, 2. There's the spring force. So the spring force is what's called a restoring force, right? It wants to pull the spring back to its natural position. So anytime a spring is stretched beyond its natural position or compressed out of its natural length, it wants to get back to it, and it exerts a force linear, so it's proportional to the amount of distortion. So it's a linear restoring force. So the spring force is Fs, and it's proportional to how far the spring has been stretched past its natural length. So that's going to be L naught, which is the amount that it got stretched from its natural length to its equilibrium position, plus how far it's gone beyond its equilibrium position. So L naught is the stretch to get to equilibrium, and y of t is how much it's gone beyond that. So this
It's not like L naught. L naught is really just a distance.
L naught is this distance from the natural length to the equilibrium position. This is a way of saving, there's a whole lot of like annoying symbols that go on if you don't just call this L naught. You can still track it, but it's way more obnoxious to have the 0 line be the natural length of the spring instead of the equilibrium position. I mean, ultimately we want this to be equilibrium because the natural behavior of this mass is it's going to oscillate around its equilibrium position, and so that should be the center of the oscillation.
But why is it not L naught plus the natural length? Because is that not where
So if you think about, like, if nothing was moving, this is how this would sit, right? And so even at equilibrium, there's already a force that's being applied here. In fact, we're going to write this down for later. So in equilibrium, it must be the case that the gravitational force and the spring force add up to 0, right? If there's nothing moving, then the first law would say no moving, no force, right? The forces must balance completely. If that's in equilibrium, not moving, that must be true. So it must be true that K times L naught plus mg is equal to 0. I'm going to write a minus here. These forces point in opposite directions. This is the force of gravity, and this is the force of the spring trying to pull the thing back to its natural position, right? And there's this y of t is not here in equilibrium because equilibrium position is 0. So that is the balance of forces there. So if it happened to be the case that as we're deriving things, if I ever saw an mg minus k L naught, I would know I could replace it with a 0. That might be relevant later. Okay. So in equilibrium, again, to emphasize here, in equilibrium, what we're saying is mg and minus k L naught have to be perfectly balanced or the spring would be moving. Okay, the negative here is here because we want the force to act in the opposite direction of the displacement. If it's stretched too far, we want the force to pull it back towards the natural length. If the spring gets compressed, we want it to push out. All right, more forces at play. So we're also going to consider the force of damping, and we're going to make a big assumption here. This is our third force. So damping. Damping includes all kinds of stuff. We have friction, air resistance, material distortion, the conversion of mechanical energy to heat energy. Okay. Anything that bleeds energy out of the system. Anything that acts to bleed energy out. So that's called a damping force. So friction, air resistance, material distortions, mechanical properties, conversion of mechanical to heat energy, all of that stuff is a conversion of the energy of oscillation into nothing. We are going to make the assumption here that our force of damping Fd is proportional to the velocity of the mass. Now, when we did air resistance way back at the beginning of the class, I made you a model where we assumed that air resistance was linear with respect to velocity. I said that's not really a realistic model. For small values of velocity and small distortions, it's fine. The same thing is happening here. We are making an assumption, a modeling assumption, that damping force is proportional to velocity in the opposite direction of velocity. So if you're traveling this way, the damping force is going the other way because it's bleeding energy out. Okay? A more realistic analysis here would say that, I'm going to call this C, not K. Sorry. Damping constant, C. All kinds of crap is piled into that C. Every single bit that's happening here is piled up into some sort of usually empirically measured constant. So this is a major assumption. It's not realistic in practice because in practice I think typically this is the square of velocity that it responds to. But by the same token, Hooke's law, springs do not respond linearly to their distortions. They respond in all kinds of weird ways, and the spring constant changes as you can think. Springs get really soft as you get them really stretched out, right? So in your later classes, you will learn way worse models for this. But at least from the standpoint of modeling in an easily understandable way that you can add more terms to later, these are reasonable assumptions to make. Hooke's law says it's linear for small distortions from equilibrium. And this says, as long as velocities stay relatively low, this is a reasonable way to model damping forces. All right, so the final possibility is that you can have an external force, which is sometimes called a driving function. Or a forcing function. And we're going to focus specifically, so if you want a model here, that would be if I hooked up some sort of motor to this thing that could impute some kind of force to the system while it was oscillating, that's what I mean by an external force. We're going to specifically look at the case where our external force, which is just capital F of t, is going to be some kind of trig function. So we're going to look at periodic forcing. Those are the most interesting things to consider. If you like an example of periodic forcing that shows up in practice, we live in a country with AC current in the walls. AC current is an oscillating current that flips back and forth with 60 hertz. So every circuit that you hook up to the wall is experiencing a periodic forcing function. Of course, a lot of them immediately convert that to a DC current, but you can actually do that with what we're going to be studying here. Okay, so what Newton's law says is that if I have all these forces that this mass is being subject to, that the total force is just add them all together. Let's just do that. So total force, F tot, is equal to the force of gravity and the force the spring is exerting and the damping force and the external driving force. That is the total force that's being experienced by this thing. On the other hand, Newton's second law says, since we are studying an object in motion, Newton's second law says actually the total force should be equal to the mass times the acceleration. Or if you like, my double prime, the second derivative of position. So if we chain those together in a move that may be familiar to you for your, like, if you've ever done endless derivations in a physics class, we're going to write down that my double prime, which is equal to the total force, is also equal to, okay, force of gravity was mg, the spring force was minus k times L naught plus y, the displacing, or the damping force was minus c times y prime, and then we have this f of t term out here. So fg, fs, fd, capital F of t. On the one hand, it's mass times acceleration. On the other hand, it's all of this stuff all added together. So already we should be able to see that this is a linear differential equation with constant coefficients. So if I multiply everything out here, and I write this out, now I have my prime prime is equal to mg, and I'll distribute the k through there, so I get a minus k times L naught, and a minus ky, and a minus cy prime, and an f of t. Now that looks pretty familiar. Isn't this like mg minus kl naught? Haven't we seen that somewhere before? Oh, that's the balance between gravity and the spring force at equilibrium. Those must be equal to each other, which I wrote that down over there. So this disappears, and you end up with my double prime plus cy prime plus ky is equal to f of t. And we can go one step further, which is pretty typical, which is to write this as y double prime plus c over my prime plus k over my is equal to 1 over m f of t. And this, once you stick it together with y of 0 is equal to y naught and y prime of 0 is equal to v naught, this dude right here is called the mass spring equation. So all that time that we spent studying linear differential equations with constant coefficients in the homogeneous and non-homogeneous cases, as special case as that seems, right? Like, we shaved off this really specific example to look at. Part of the reason to look at it is one of the fundamental equations of engineering and applied mathematics is a second-order linear differential equation with constant coefficients. And anything that an engineer or physicist can turn into a simple harmonic oscillator, you do. Because these are easy to understand, they're easy to model with, and they're easy to understand the solutions of. So we're going to write down some simple cases now, trying to analyze how this thing can behave. So this is going to look like we're doing 8.2 and 8.3 again, but what we're going to be trying to do this time is not just to do the math to solve the equation, but to physically interpret what it is that we're looking at. So here's an example, the easiest example. So let's make the assumption that we have no forcing function and no damping. This is called a simple harmonic oscillator. So undamped, unforced. So I write down an equation like y double prime plus, okay, I'm going to work in symbols for this one because it's easy. Y double prime plus k over my is equal to 0. There's no damping term, so the c is equal to 0 because there's no damping, and there's no forcing function. And I think it's an easy mistake to make to think, well, nothing is going to happen here because it's equal to 0. But remember, I'm allowed to induce initial conditions. If I roll up to you with a spring and a mass, and you don't touch it, yeah, it's just going to sit there, right? But if you take the mass and you stretch it and then you throw it, it's going to move, right? And that's what these are supposed to take care of. Yeah, the equilibrium position is don't touch it. And the solution is not very interesting in that case, which is y equals 0. It doesn't move. So if you go through the process that we did in 8.2, you would write down the auxiliary equation, r squared plus k over m is equal to 0. And so r is equal to plus or minus the square root of k over m times I. Because of the way we set these equations up, we're essentially, now, you should be thinking already, okay, so there's this model has promise because it looks like it's unavoidable that we get cosines and sines here. If k and m are both positive constants, this must have complex roots, which means the answer must be sines and cosines, which is exactly what we see when we in a simple harmonic oscillator, right? I mean, the masses go like this. So oftentimes this quantity right here in different classes is called omega naught. So omega naught, which is equal to the square root of k over m, is sometimes called the circular frequency. It's not really a frequency because there's no 2 pi involved, but like this dictates the frequency of the solutions that come out. And if you just follow what we did last time we did this, this will tell you that the solutions to this equation must be of the form, okay, so y general is equal to c1 times the cosine of the square root of k over mt plus c2 times the sine of the square root of k over mt. And no additional work needed. You just have to identify that you've got a complex root. This is what it turns into. So these oscillate with constant amplitude, constant frequency. So if I was going to ask you an exam question to see if you could analyze this at all, I might ask, okay, what if you built one of these, a system like this, and it was oscillating, and then you took the mass off and you replaced it with a mass that was 10 times larger? What would happen to the frequency of oscillation? It would decrease, you said? The frequency is going to decrease? What do you mean by decrease? Well, let's take a look and see. This is actually, I'm going to verify if your answer is correct or not. Okay. So let's look at just a real simple case, like the cosine of t and the cosine of 10t and the cosine of 1 over 10t. So I've got 3 different things to graph here. What I want to look at is, what is the effect of screwing with this number? So if m got really big, this number is going to get small, right? We're going to go from this picture to that one. If m gets big, that number gets small. Well, cosine of t in the period from 0 to 2 pi, I guess looks something like this. And the cosine of 1 over 10t, what is the period of the cosine of 1 over 10t? How do I find a period?
2 pi over
2 pi. So period is equal to 2 pi over b, which in this case is 2 pi over 1 over 10, which is 20 pi. Oh man, so like it's trying. It'll get there eventually. So it's kind of like somewhere out here, 10 times further down the line, it will do its first cycle, right? So that's the cosine of that's this guy. So the period here is 20 pi.
Why did that start at 0?
Oh, because I'm an idiot.
Okay.
It's like, it doesn't suddenly turn into a sine. Yeah, sorry. Okay, how about the cosine of 10t? What is its period? Pi over 5. So it's going to go like 4, 5, 6, 7, 8, 9, 10. There you go. Okay. So when this number gets, okay, last question. What is the relationship between period and frequency? Inverse.
Inversely proportional.
I don't like the word inverse when we're talking about scalars. What's the better word for when we're talking about scalars? I'll try. Okay, yes, multiplicative inverse. I was going to say reciprocal is the word I was after, right? Frequency and period are reciprocals of each other. It's only inverse because we're talking about numbers. So the shorter the period, the higher the frequency. And the longer the period, the lower the frequency. So what this is telling you is if m got really big and you slide from this case to this one, then the period gets longer, which means the oscillations are going to slow way down, right? There's going to be way fewer of them per time. What if you make the spring stronger?
Speeds up.
Yeah, if you make the spring strong, so I take off a little weenie spring and I put a big beefer in there, then the K gets really big, right? Spring constant can exert more force, and you would expect the oscillations to increase in frequency. Okay, I will tell you that when you're tuning the little knob on your radio, essentially what you're doing when you turn the knob on your radio is you're adjusting the K value in the electric model, right? You're adjusting the spring constant of the circuit by adjusting the resistors. Okay, so that's the basic case. What if we have a more interesting model? So somebody comes along and says, okay, well, we're not in chapter 8.3 anymore. Now we're in chapter 8.5. So I'm going to write down an 8.3 problem. Y prime prime plus 9y is equal to the cosine of 3t. And I want you to think about that physically this time. Not just from a mathematical solve the equation standpoint, but physically. So what are we doing here? We have a mass spring system. It is undamped because C is equal to 0, so no energy is going to leave the system from the damping force. And what we have instead is that this system is being driven by a periodic driving function, or forcing function, with a circular period, say, of 3. And if we just go through the process of checking in with what we think the homogeneous solution should be to this, so using our 8-3 techniques to give the general solution, we write down y prime prime plus 9y is equal to 0, so r squared plus 9 is equal to 0, so r is plus or minus 3I, which means our homogeneous solution yh is c1 cosine of 3t plus c2 sine of 3t, and already from a physical intuition standpoint, you should be cautious. Because you have a system that wants to respond with the same period, or the same frequency. Its natural response is with the same frequency that you're driving it with. So this system cannot bleed energy because there's no damper, and you're contributing energy at the exact frequency that it already wants to oscillate. So your physical intuition should already be telling you I should worry about resonance in this case. So I'm worried about resonance. Now, how am I going to confirm that resonance is a possibility? I'll just solve the equation. The second part of 8.3 says, what am I supposed to do now to solve the particular problem? I guess a particular solution. A cosine of 3t plus b sine of 3t. That's my trial solution. And then I look at my trial solution, I go, dang it, my trial solution and my homogeneous solution are the same. So if I went through the trouble of plugging this into the differential equation, I would get 0 is equal to the cosine of 3t and be mad at myself for not noticing. Right? This guess for the particular solution will be eaten by the left-hand side of the equation, which means you need to modify your trial solution. And you need to try a particular solution is a t times the cosine of 3t plus b t times the sine of 3t. So I'm not actually going to work through the solution to this directly right now because I don't want to blast you with algebra. But when you're done, this is going to work, and you're going to be able to find the a and the b that solve this thing, right? You just take the prime and the double prime and you plug them in, and you can see what the solution should be. This will solve the equation, this modified one. And when you write down your general solution, yg, you're going to get c1 cosine of 3t plus c2 sine of 3t plus at times the cosine of 3t plus bt times the sine of 3t. So this part, YH right here, acts like this. Whatever its whatever its amplitude is, it just stays the same amplitude. It doesn't change. It's got constant amplitude. What does the other one do? There's T's in here. So this one acts like this. The system cannot bleed energy. So the forcing function continues to add with constructive interference, the forcing function continues to add energy to the system, and the second part of that solution is being driven as an expansion. So you're getting wildly improved, not wildly, but linearly improved. This is bad, right? Linearly, if you have oscillations that are like increasing like a line, there's like in an uncontrolled way. I think last class somebody asked me, well, it doesn't make any sense. You could get a perpetual motion machine. And the answer is no, you don't, because what happens is everything breaks first. Right? Your spring falls apart. Springs do not like this. So pretty much everything you have with a spring in it has caps to like limit how far the spring can stretch. Okay. So this is generally going to be the case, right? So one analysis to be done here is if you are in the case where you have an undamped oscillator with a forcing function and the frequency of the solutions, this quantity right here, which is W naught, and this quantity right here, which is, omega naught and omega, if omega is equal to omega naught, if the natural frequency of the system corresponds to the frequency that you're forcing it with, bad things happen. Also in circuits. Last time we talked a little about what happened what if these were just really close to each other? Kind of, the kind of false resonance, right? Beats, if you like music, it's beats, right? You get solutions that sort of explode and then come back together, and then explode and come back together, because you get lots of constructive interference that flips into destructive, and then back to constructive and back to destructive. So even in the case where this is close, you have to be careful. All right, so the last case I want to look at today is, and I will point out, I am not interested in you, if you go and look at these notes, and you look at all the stuff in the back half where it's like, look, there's all these cases and equations that have lots of constants in them where you don't have to solve anything. This is the worst possible way to do this. The easiest way to do the analysis we're doing here is just to solve the equation using the techniques we learned in 8.2 and 8.3 and then analyze the solution. Don't try to memorize a bunch of stuff that's like harder to learn than just solving the equation. Okay, that's especially true, for example, like the last case here. So the last one I'm going to look at is a situation that looks like this. And this is something, I'm going to put the math down, and you may not believe the answer until you've seen it demonstrated in the lab, basically. So maybe you guys have seen this already. I'm going to write down the equation y prime prime plus 2y prime plus 9y is equal to the cosine of 5p. The first thing that I notice here is the presence of a damping force now. So there's damping involved in this equation. And we also have a forcing function. If the forcing function wasn't there, then no matter what I did to the original system, it should decay to zero in the long run. It has to, right? That's what the damper does. It eats the oscillations of the system and drives them to zero. So let's verify now what I don't know yet is if I drive a system with a forcing function and there's a damper, what is the long-term behavior going to look like? In a circuit situation, that would correspond to something like I have a television or a radio or something hooked up to a wall current, and I slam the power on, that gets flooded with an instant hit of current, right? That's like an initial condition, like distorting a spring. That's like going to hit this natural term. What should happen there is that dampers in the circuit should eat that initial current surge, and what you hope is that the circuit falls into some kind of predictable behavior, maybe corresponding to something to do with the forcing function. With a spring system, you can think, if I have a driving motor hooked up to something, what's going to happen? Does it matter? This is a really interesting question to think about. Does it matter if I don't touch the mass in the beginning. If you don't touch the mass and turn on the motor, you expect it to act like the forcing function. What if you do touch the mass first? I just pull it way out and I throw it. What's the long-term behavior going to look like? So let's take a look. If you write this down, we're going to solve y prime prime plus 2y prime plus 9y is equal to 0. So r squared plus 2r plus 9 is equal to 0. So r squared plus 2r plus 1 is equal to minus 8. So r plus 1 squared is minus 8. And so r is equal to minus 1 plus or minus the square root of 8i. You don't have to do it this way. I'm just doing it because I like completing square. Okay, complex roots. You have to remember that if you ever have a plus or minus ib, then your homogeneous solution looks like e c1 e to the at cosine of bt plus c2 e to the at sine of bt. If you remember that, then you can read off from the roots here that the homogeneous solution to this equation, the natural behavior, looks like c1 e to the minus t cosine of the square root of 8t plus c2 e to the minus t sine of the square root of 8t. What happens as t goes to infinity?
Goes to 0.
Yeah, we get these e to the minus t's in here, right? E to the minus t is going to 0 pretty damn quick. So whatever this is doing, these oscillators are doing, the e to the minus t in front is driving them to 0. This solution, as t goes to infinity, yh of t tends to 0. This particular one kind of looks like this. You got oscillators that are sort of doing that kind of thing. So solutions that disappear as time goes on are called transient solutions. They're here for a while and then they decay. All right, so second step. Let's look at y prime prime plus 2y prime plus 9y is equal to the cosine of 5t. And now using the methods, we've used 8.2 to solve this equation. Let's use 8.3 to solve that one. What should I pick for my trial solution this time?
A cosine 5t plus b sine cosine 5t.
Do I need the t's? I'm asking you. Do I need the t's this time? How did you know you need to modify a solution to a differential equation? Do you remember? So last time when we did this, we picked a particular solution and we compared it to something and we noticed that we couldn't use it, right? What did we compare it to? So this guy. So we compare this to a homogeneous solution, right? We have a particular guess, we compare it to a homogeneous solution. David, do I need the t's? Hold on, you've already answered. I have your answer. I'm testing your answer right
Oh, that's right. Sorry.
now. Barrett, do I need the t's?
I'd say no.
Okay, why not?
Because it's different from the homogeneous.
It is different from the homogeneous solution. So generally the rule is when you're solving one of these equations and you have a guess for your particular solution based on the output. So this guess is based on this forcing function, right? This non-homogeneous part. When you look at the non-homogeneous solution and you try to guess the particular, the only possible pitfall to this is if this and this match each other. If this and this match, it means if you tried to do the math on this one, it would get eaten up by the homogeneous solution and turn into 0. So the only time we have to worry about modification is if we have matching between our outputs and our guesses. So when you're looking generally at these equations, if I have stuff like, where I'm going to start getting worried is if I have things like this, y prime prime plus 4y is equal to the sine of 2t. This kind of thing is I have to worry about because it's possible that when I solve the homogeneous equation here, when I get started, if I did not solve the homogeneous equation first and I was just trying to guess a particular solution, I might guess yp is equal to a cosine of 2t plus b sine of 2t because that's what the output to this equation is. This is a thing I could plug in over here that would make cosines and sines that have 2t's inside of them. If you did this first without solving the homogeneous equation, you would plug these in and you would not get a solvable problem out the other side. And the reason is, if you solve the homogeneous equation here, if you read off the auxiliary equation and solve this, you would have c1 cosine of 2t plus c2 sine of 2t. And to be a homogeneous solution means you get turned into 0. Anything that looks like this gets turned into 0. So yeah, these get evaporated. If you guess this, it's not going to work because that is the exact form that gets turned into 0. And so in the case where we have overlap between the guess that we want to make and the thing we already know gets turned into 0, these are the things that we modify. So I'm not going to modify here because when I compare what I want my guess to be to the things that get automatically turned into 0, I'm cool. I don't need to worry about this getting turned into 0. This is going to work. Okay, now, I didn't tell you guys, but it's against the rules to take 3-day weekends and then forget all the math that we crushed in at the end of last week. So that's not one of the things you're allowed to do. You're also not allowed to be in a class that like goes at this pace. I don't know who let you do that. That was against,
Is anyone also allowed to forget the math?
Yeah, no, you're not allowed to do anything. You have to remember every single piece of math you ever learned in whatever period of time you had to learn it in. Except you have less time to learn it than you actually need. So, okay. So the upshot of all this is a good guess for the particular solution. And this is the physically observed thing that I think is kind of weird. If you take a system like this, and you have a motor driving the system, some kind of forcing function with a certain period, and you take the mass and you pull it to any initial displacement you want and induce any initial velocity you want, the general solution to this is going to turn out to be your y general is going to be the sum of your homogeneous solution and your particular solution. C1, hold on, let me get this all out. So we got C1 e to the minus t cosine of the square root of 8t plus C2 e to the minus t sine of the square root of 8t. That was our homogeneous solution. Plus, you could, in practice, solve for this a and b. I don't want to do the algebra right now. I'm going to make you guys do that. A cosine of 5t plus b sine of 5t. That solution will work. This bit right here goes to 0 as t goes to infinity. That's called the transient part. That just vanishes. Whatever you did to the system at the beginning evaporates. Whatever impact that you had on the system corresponding to the initial condition goes away. And what's left is called the steady state solution. And the steady state solution has the same frequency as the forcing function does. So no matter how you affected the system at the beginning, whatever you did to it, that behavior is destroyed by the damper, and all that's left in the end is oscillation due to the external force. And the reason that that's a thing that we want to use in practice is, again, a good model here is, if you have anything, we live in a country that has alternating current, if you plug anything into the wall, the forcing function on the circuit, the thing that's driving the mass spring system, is a 60 hertz oscillating signal. It's just flipping back and forth like a periodic function. And when you turn something on, there's all kinds of protections in every device that you turned on so that this happens. That initial surge of current that goes through the circuits of the thing just dissipate as quickly as possible so that the behavior of the system settles into whatever, so it's responding just to the wall current and not some crazy current surge. So when I was a kid, when you turn on a TV, like it took forever for the TV to come to steady state. You could physically watch the thing come up to power, right? Like where it would settle into the way it was supposed to act because all the transient behavior was gone. But I mean, it was measurable. 30 seconds, the TV warming up and the screen slowly turning on, or weird sounds coming out of the damn thing. So this kind of analysis is the core of what you do with mass spring models. The computer does it, and your responsibility as the modeler is to understand what the solutions are telling you, and then usually to adjust these solutions to comport with whatever physical situation you happen to be studying or constructing. All right, so where we're going next with this is we are going to use the techniques that we learned in 8.2 and 8.3 about linear differential equations, and we are going to mix them together with eigenvalues and eigenvectors that we did with matrices, and we are going to study simple linear systems of differential equations, which you should think of as systems with feedback. Two things that are both dependent on the same variable, but they see each other. So predator-prey models are a good example of this, right? The populations of the two animals both depend on the populations of the two animals. All right,